Hello, everybody, and welcome to this week's Hubble Hangout. My name is Tony Darnell, and I work at the Space Telescope Science Institute. It makes me very happy to welcome you all back to our Hubble Hangouts here because you guys have been giving us all kinds of great feedback, and it's just been amazing. We were just talking before the Hangout. We've been doing this for 2 years now. So every week we try to bring you new science from the Hubble Space Telescope, and we are here today with yet another example of that. This week, astronomers using both the Spitzer Space Telescope and the Hubble Space Telescope have been looking at galaxy clusters, and they have found something interesting in there that ordinarily they do not find. I'm not going to give it away yet because we're going to have the astronomers tell you all about it. So now, this is ordinarily the time when I start giving out announcements and stuff, but I don't have any, because I don't think anything all that interesting was going on, so I'm not going to pass it on to you guys, but I would like to invite you guys to leave questions and comments throughout the Hangout, and we will read them throughout, and I'm going to have Scott tell you about that in just a minute. But first, I have to introduce my partners in crime, Dr. Carol Christian, who joins me. She's the HST Project Outreach Scientist. Hi, Carol. Also joining me is I almost said Dr. Scott Lewis.
No.
Scott Lewis from knowthecosmos.com and a great many other places around the internet. He's driving the internet for us during these Hangouts. And why don't you tell everybody, Scott, how they can interact with us?
Yeah, absolutely. So the best and easiest way for you to interact with us is using the Q&A app. So while we're live right now, you'll see on the bottom left of your screen some yellow text saying that we are answering questions. I've got it loaded up. Tony's got it loaded up. If you have any questions for us and our guests, or even some comments about that, you can ask that in there. And you can even +1, you can bump them up. So if there's a question out there that you like and you want to have answered, you can go ahead and recommend that. And we can select it when it's live, and it'll let people know that we are answering that question that's going on. You can also comment on YouTube and also on Google+. We have a Facebook event for this as well. And the other great way for interacting with us is over on Twitter. So as you see in my lower third here, we have the Hubble Hangout hashtag. So I've got Twitter up right now over in TweetDeck, and we'll be answering questions, and I'll be live tweeting as we're going on. So just either @mention Hubble Telescope or use the hashtag Hubble Hangout, and we will get your questions and reply to them during the show.
And I want to remind you guys that it's starting to happen more often now. People are telling me that they can't find the Hangout, and the best way to find it is to subscribe to us on Hubble Site channel on YouTube, and that will alert you when the ones are coming out live. But you guys should know by now, every Thursday at 3 o'clock Eastern Daylight Time, we are here doing Hubble Hangouts, and so you should always check out the channel there. You could also follow us, like Scott said, on @Hubble Telescope. So those are the two easiest ways to find out about these Hangouts, and you want to find them because they're becoming world famous. I was looking at the demographics the other day. Hubble huggers, Hubblers, Hubbleholics, whatever you want to call yourselves, all of you guys are all over the world watching these Hangouts, and I think I know why. We were talking about this also before the Hangout. You know why? Because where else in the entire internet are you going to learn what the mass of a blue giant star is in units of cows?
Cows.
That's right.
Or the energy of a quasar, the energy of a quasar in units of ant push-ups. These are the kinds of things, folks, we've made astronomers do in the past. And where
highly scientific.
Entire internet are you going to find something like that going on?
And now our guests have just left because
that's right. We
they
make
want to do those calculations.
We make you guys earn your degrees, right? It's yes, it's great that everybody has.
And I just want to comment. I don't know why people can't find Hubble Hangouts. It's called Google.
I know people.
Type Hubble Hangout, and there are like 5 links to YouTube, to our website, to all things. So,
yeah, I agree, but still, nevertheless, people say they search for it, can't find it. So I'm trying to help them in any way I can.
It's not rocket science.
Yeah, you know what I'm going to do in the next exoplanet hangout? I'm going to ask the guests to tell me how many chewed up pieces of gum that would fit in a Neptune-sized exoplanet. That's what I want to know next. So stay tuned, folks. We'll find all that out this week.
Yeah, that might be next week. If I can drum up some exoplanet people.
So this week we have a very interesting hangout in store for you, and if I haven't scared away my guests, although it looks like I have almost scared away one of them already, don't worry, we're not going to make you do any weird calculations this week unless...
I will. I'll make you do them.
Oh, okay.
Tony won't.
Okay. I was going to be nice, but, Scott's...
I'm never nice.
So as I mentioned at the top of the hangout, astronomers using both the Spitzer Space Telescope and Hubble, and I guess the Canada-France Hawaii Telescope, which is on the ground in Hawaii, were looking at this galaxy cluster, and they found something. They looked at something. They found things that surprised them, and I'm going to let them describe what that is. But before I do, I've got to introduce them. With me is Dr. Tracy Webb. She is from McGill University, astronomer in Montreal. Hi, Tracy, and welcome.
Thank you very much.
Also joining me is Dr. Alison Noble. She is from the University of Toronto, and Adam Muzzin from Cambridge. Welcome to both of you guys. It's good to have you on our hangout.
Thank you.
Hello. Okay, so let's get started.
And by the way, we really appreciate them being here visiting us from Italy.
Oh, really?
Italy. Yeah. They're at a conference in Italy.
Oh, you're in Italy right now?
Yeah.
Yes.
Oh, okay.
Yes, we had to clear a very busy schedule.
Yeah, we could be having a glass of wine.
Oh, you don't know how. I know
we didn't stop you from having a glass of wine.
That's right. In fact, we're gonna probably come up with a word for a drinking game soon. So you might want to stay tuned.
It would not be a first time we've had a drinking game, but drinking espresso shots. Yeah, that's the one to show.
Which is the last thing any of us need right now.
Right.
Okay, so today we put out on Hubble site, and as well as went out into the internets in general, a press release that was announcing some of these findings, some of these observations. So Tracy, I think I'd like to start with you, but I also want to, we always wait too long to put up images. So Scott, if you'd go ahead and put up this image. This is a galaxy cluster. And Tracy, can you describe a little bit what we're looking at here?
Yeah, so what you're seeing is, I guess, a side-by-side image. Obviously, but I'll just make it clear, the image on the right-hand side is a zoom-in of the image on the left-hand side. And the image on the left-hand side is a close-up of this galaxy cluster that myself and my collaborators discovered. You can see a lot of we can explain what a galaxy cluster is in a minute, but it's essentially a conglomeration of many, many galaxies held together in space by their own pull of mutual gravity. And we can see a lot of the clusters there. The cluster members, shown as kind of red galaxies. But the thing that we were really surprised to see is that funny J-shaped object that seems to run in between two of those kind of red galaxies, which is highlighted on the right-hand side.
Okay, let's get to that in just a minute, but let's go back to let's take a step back, and you were already on the right track by describing what these galaxy clusters are. What is the name of this thing? It has a name that I'm afraid to say.
It is called Sparks 1049 plus 56.
Ah, okay, and it's called that for what reason?
It's called that because it was discovered as part of a search or a survey for galaxy clusters, which is called Sparks, and Adam can tell you a lot about Sparks because that's his baby. Sparks stands for the Spitzer adaptation of the Red Sequence Cluster Survey.
Ah, I love acronyms like that.
Yes,
okay.
So it's an acronym within the name.
That's right, acronyms all the way down, recursive acronyms, yes.
So the Sparks is the name of the survey that it was found within, and then 1049 plus 56 is just a short handle for its coordinates, celestial coordinates in the sky.
Do you guys say it that way when you're in like meetings and stuff? Do you go, you know, that is, I was looking at Sparks 1049 plus 56, and I saw.
So for the longest time, they were just calling it Tracy's cluster, which I really liked.
Oh, that's really good. Tracy's cluster.
Yeah, that would work.
But
I'll do some graphic design after the show, and I'll make sure you have your
call it, okay. In short form, we call it 1049.
Okay. Well, Tracy's cluster, we're going to call it Tracy's cluster on this hangout now. So Tracy's cluster, it has, according to the press release, has 27 galaxies in it, and it's pretty massive. How many suns would that be?
Well, so first of all, we've only confirmed 27.
Oh, there may be more then.
There's probably lots more because it takes a long time on a telescope even just to get one member confirmed. So we've confirmed 27, but there's probably lots more. I'm sure, many hundreds. But in terms of the overall mass of the cluster, we estimate it to be a few, so in scientific speak, a few times 10 to the 14 solar masses.
Important part being 10 to the 14.
So 10 to the 9 is a billion, and this is 10 to the 14 suns.
Okay.
But that includes, all of the galaxies, all of the gas, and all of the dark matter.
So we are into the trillions, and it is, and these things are pretty far away then, right?
That's right.
Roughly according about 10 billion light years. And for those of you who want to see it in the sky, you have to look in the constellation of Ursa Major.
That's right.
So that's sort of what we're talking about. Adam, let me ask you about the SPARC. What is the SPARC survey then? Is that something that is looking at the word survey tends to imply an entire looking at big areas of the sky? Is that what it's doing?
Yeah, actually, so SPARC's used a combination of data from the Spitzer telescope and the Canada-France-Hawaii telescope. And basically the way that what we did is we took pictures of the sky over a fairly large area from both of those telescopes. And the idea is that if you want to find very distant galaxy clusters, the galaxies that you find in them tend to be very red. And so you look for things that are sort of very red when you take pictures between Canada, France, and Spitzer. And if you can find those, and they're also bright and in big clumps, those tend to be galaxy clusters that are very, very far away. So the point of SPARCS was to find these kind of things, very distant galaxy clusters, amongst the most distant that we can possibly find.
Oh, okay, and I want to, Tracy, I want to come back to you in a minute about this, getting these things confirmed, members of the galaxies. But before I do, Carol, let me get you on. I'd like to get you to talk. You said before we started, you know a lot about the Canada-France-Hawaii telescope and Spitzer. So why don't you tell us a little bit about these instruments? What are they like?
So this Spitzer is a space telescope, which is one of the great observatories like Hubble. Chandra is the X-ray great observatory. Spitzer is roughly the infrared. Hubble is the UV optical, although it has a little infrared. And then there was a gamma ray observatory, and those were called the great observatories. And the three, Chandra, Spitzer, and Hubble, are still in orbit, and they are often used in concert to do multi-wavelength studies because, an object might have X-rays, might be visible in the infrared, want to compare to Hubble. And Spitzer is something like 33, 34-inch diameter telescope. It has a number of instruments on it, and mostly looks in the infrared. So it's really good for looking at some of our favorite things, distant galaxies, exoplanets, and also the center of our galaxy or in other parts of our galaxy, because the infrared looks through the dust. Infrared also, as Adam was just saying, can help find things that are very far away because of the reddening and the expansion of the universe. Canada-France is actually a ground-based telescope. It was built by Canada, France, and the University of Hawaii. It's on Mauna Kea in Hawaii. I worked there for 9 years. And it's actually a magnificent telescope, and it has lots of capability. It has imaging capability because the sight is really good. Not as good as orbiting satellite telescopes, but in its day, it did some pretty darn good imaging, and it's still really good imaging, and it also does spectroscopy. And so it's always helpful to have ground-based telescopes because you can they're useful because you can change instruments more quickly, and if you build new ones, you can put them on a ground-based telescope more quickly than you can putting one. And we're not servicing Hubble anymore, and we never service Spitzer, and we never service Chandra. So Canada-France has a really good suite of instruments for this kind of work.
Yeah, a lot of people don't know this, but while infrared astronomy is best done in space, there are some places on the planet that are very good for doing infrared astronomy. The requirement being you need it to be very dry. You need to have very little water vapor in the atmosphere so that the infrared can get through. And in Hawaii happens to be one of those places. Even though you think of Hawaii as a humid tropical environment, at 14,000 feet, it's pretty dry up there. And the same is true for the high in the mountains of Chile, which you see a lot of ground-based telescopes.
Exactly. And back in the day, we used to go up to the telescope and do the observations. And I'll tell you, there's nothing better than coming out of that, 4 days of dusty environment, going straight to the beach.
Get the bends going the other way. Well, that's amazing. So, but what do they do now? You said back in the day they did that. What do do they still go up to the?
No, largely the observations. I'm not sure what Tracy and collaborators did, but our friend Gordon Squires was just out there 2 weeks ago observing, and they observed from God's country, Kamaweala, Hawaii, or Waimea. From either CFH, CAC. There's a bunch of observatories, and they often observe from a more habitable place where you can actually get food and like water and stuff like that.
So don't get altitude sickness going up. I was just there a little while ago too, and the observatories for Keck out there it's like out in no man's land, but it's still great because you still have access to everything as opposed to being in no man's land.
Hey, there's a Starbucks
really
across the street from Keck.
Well, I need to go back then because that would be awesome.
Wow, you don't get that.
I need my soy latte now.
Exactly. For example. All right, we digress.
Don't get that in space, Spitzer. Okay. So, all right. So, Tracy, I want to go back to something you had said about these galaxy clusters and getting members of them confirmed. You said that was kind of a big deal, but that there were only 27 so far, but you think there's hundreds. I don't understand Adam was just telling us about the survey itself. They presumably identify these clusters pretty quickly. There's a big old chunk of them there, and but then you said that getting the individual galaxies confirmed is kind of a big deal. Why don't you talk a little bit about what's involved in that?
Right. So if we want to know what Adam finds is essentially the location of one of these galaxy clusters. He sees like a big overdensity of galaxies in his survey, but we don't know right away which individual galaxies in that overdensity are actually part of the cluster. Because if you think about it, what you're seeing when you look at the cluster is everything that's in front of the cluster and everything that's behind the cluster and everything that's in the cluster all projected onto one sort of two-dimensional image. And so just by looking at it, we know that most of the galaxies that we see in that image are probably cluster members, but we know that there's also some contamination. So the way we actually the way we confirm that a galaxy is within the cluster is by measuring the distance or the redshift to that particular galaxy. And so we do that by obtaining spectra for the galaxy. So we need a really, really powerful telescope that can provide really detailed measurements of the emission or the absorption lines in the galaxy spectrum. And for that, we actually used another ground-based telescope, which is the Keck Observatory. And so we have to go out and measure an individual distance to every single galaxy in that image that you see there and see which ones are at the distance of the cluster and which ones are either in the foreground or in the background, and basically separate it out into like a three-dimensional image. And so each one of those observations takes a long time.
I see. So that's what you meant. Okay. So with redshift, we've talked about that at least 153 times on these Hangouts. So it's a number. It's just a way in which we find out how far away these galaxies are. The bigger the number, the farther away they are. The galaxy record of Hubble has been somewhere of about Z equals 11, something like that, which is pretty darn far away. But Frontier Fields is hoping to break that record too. So anyway, that's just a number of how far away things are, and it's a time-consuming measurement. Now, you guys said you used Keck to get that done, but So Alice, Allison, let me try to get you into this conversation a little bit. Haven't heard from you yet. Why don't you describe for us a little bit about what your role is, what your interest is in this, and some of the things that you've noticed about this galaxy cluster.
Sorry, you broke out for a second.
I did?
Up for a second.
Oh,
yeah.
oh, sorry. I wanted to try and get you involved in the. I wanted to get a sense of what you were doing as part of this team. What your interest is, and what about this galaxy cluster got you going?
Right. So we've only just started to talk about some of the wavelengths we've looked at this cluster, but we've also looked at it at the far infrared all the way through far infrared and submillimeter wavelengths as well, and that's kind of where my role comes in, is looking at some of these longer wavelength emission from the cluster and the galaxies in the cluster. So we talked about Spitzer, that we have MIPS 24 micron imaging, but we also have another space-based telescope that we're using, which is Herschel.
Yes.
Which is no longer.
That's an ESA scope, or was.
Yes, was, yes. So it's no longer running, but there's a bunch of archival data from Herschel that you can download yourself and reduce the images. So we use that, the archival data, to get 3 additional wavelength measurements of one of the galaxies in this cluster that I'm sure Tracy's going to talk about a bit more. So it's the brightest cluster galaxy, which is kind of the main focus of this paper. And then additionally, we also got imaging from a submillimeter telescope, also on Mauna Kea, called the JCMT.
Man, you guys hogged up everybody's time, didn't you?
Yeah.
These people live right? They go to conferences in Italy and they observe in Hawaii. I was like, really? Get serious.
And actually,
we need to get into the galaxy cluster game.
You still go up the mountain for JCMT, which is kind of nice.
Yeah.
You don't have a Starbucks, but you do get to see the Mars-like landscape on the top of Mauna Kea and spend 14-hour nights observing on JCMT.
There it is. Scott's got a picture of it there. So
yeah,
staring at us from the top of, not at us, but at the sky, from the top of Mauna Kea. So, okay, well, so you looked at, Scott, would you please put back up the cluster image again? So Hubble had something to do with this. We're going to get to that in a minute. But first, you looked at it with Spitzer as part of this survey, went and used the CFHT to kind of go back and verify things. And so, Tracy, go ahead. You said the thing that interested you the most was this little squishy thing in between these bright blobs there. I know this is extremely dense jargon I'm using here, but but this squishy thing is what intrigued you. What is that a galaxy being lensed? What is that?
Well, okay, so let me back up. So that is seen only in the Hubble image. So that was when we actually knew that we had something really exciting before that from the Spitzer imaging that Allison was talking about, which gives us measurements in the mid-infrared, so at 24 microns. And that's a wavelength that comes from dust that's heated by very young stars. And it's a really good, if you want to know if there's star formation going on in a galaxy, a really good way of determining that is to look at it at these 24 micron wavelengths, because if there is star formation going on, the whole thing will just glow.
Because it's hot. There's a lot of hot stuff going on there.
Exactly. Exactly. And the star formation generally occurs behind these, I like to think of them as big cocoons, and the cocoons of dust, and the dust absorbs the light from the baby stars and then radiates it away in the infrared, just like you and I radiate in the infrared. And so we...
Some more than others.
Some more than others.
Sorry, no. So Spitzer looked at this first. You saw a lot of heat going on there, and that caught your attention.
Right. And that caught our attention, and so then we wrote a proposal to the Hubble Space Telescope, which essentially wanted to see what was going on. We wanted to know why there was so much star formation happening. And when we took the image with the Hubble Space Telescope, this is the image that we saw. I don't remember what you called it now, but the long blobby thing
I've called it squishy,
the
but
squishy
you're the astronomer, so if it's blobby, then we'll
it's
defer.
both. So if you look at it carefully, you have to kind of squint your eyes a little bit, but it is a long tail which seems to be coming out of one of the very bright galaxies that you see there. And there's sort of clumps all the way along that tail, and then it finishes off in this kind of backwards J structure, which also has lumps in it. So there's both diffuse emission, and the whole thing is very long, and then along its length there's all of these clumps. And we could only see that with the extremely high resolution of the Spitzer Space Telescope. It was completely invisible in all of the other imaging that we had. And so this was really exciting because this is a sign that something very violent has been happening with this object. Something in this object has essentially been ripped apart, and it's been pulled apart along what we call this tidal tail. And there's new stars which are probably being formed all along it because of this very violent process.
So which red blob are you thinking this is a part of? The one in the upper right or the lower
one
left?
in the upper right. So so this was part of the really hard work. The blob in the upper right, which is circled, is...
Way to go, Scott. Good cue.
I'm a professional, Tony.
You are.
I'm a professional.
I'm amazed.
That's what we think is what's called the brightest cluster galaxy, which is, as mentioned here, the central cluster galaxy. So it is a huge, massive galaxy which is sitting at the very center of this galaxy cluster. And it's different than all other galaxies in the universe. So most galaxy clusters have one of these hulking giants sitting in their very centers. And so we think that the tail is kind of emanating out from that object. So if you trace it all the way back, you can see it sort of curls its way back into that object. Just for interest, there's two bright blobs to the lower left, and those are actually, they have nothing to do with the galaxy cluster. We've confirmed using Keck that those are things that are actually seen from the foreground.
Oh,
so
good. So those you've got
redshift. We got redshift. Those, yeah.
Ah, okay. All right. Interesting. That's very interesting. Because it looks like, at first glance, in the line of sight, that they are all really close together.
Well, that's what we thought originally, and it was a lot of hard work to show that they weren't. And they're just kind of, they're actually frustrating. They're in our way.
Yeah. You think nature would be a little more accommodating with some of its secrets. Well, okay. So now this was something you kind of didn't expect to find, right? That's sort of the impression I get from reading the press release. You guys weren't expecting this? Or this isn't common? That's
right. So to my knowledge, this is only the second example of this kind of thing. This kind of thing meaning this very violent, ripped-apart galaxy sitting at the center of a galaxy cluster that's this large. Usually when we look, so I mentioned that every massive galaxy cluster has one of these hulking galaxies at its center, and these are not only the most massive galaxies in the universe, but some of the oldest. And by old, we mean they formed their stars a long, long time ago, and they haven't formed any since.
So like elliptical galaxies?
Exactly. They're the biggest elliptical galaxies in the universe.
Now, are these clusters, let me just interrupt you real quick to make sure you said there's usually a hulking mass in the center of these. Are they gravitationally bound to it, or is it just loosely, are they loosely connected? What's the connection there?
You mean the galaxies with the brightest cluster galaxy?
Yes.
Well, the whole cluster is bound together by its dark matter, essentially, and the brightest cluster galaxy sits at the very center of that dark matter distribution.
Okay.
So they're all bound together.
Okay, good. Thank you. Okay, so this was something you didn't expect to see as right. Violently.
Well, so as far back as we've looked, almost all galaxy clusters have these massive galaxies in their center, and these massive galaxies look old. So it's a real mystery in astrophysics. One of our big questions is how and when did these things form? Because we figure if we keep looking back in time, deeper and deeper images, we should at some point see these things forming, and that is yet to happen. And so this was one of the first images that actually caught one of these objects in a phase that we think is a phase related to its formation. And that is this violent phase of ripping apart one galaxy to cannibalize it and then forming new stars as it does that.
Okay. Well, I want to get to this topic or this concept. I'm not quite sure how to make the segue, but there's this thing that was mentioned, and we've had a hang on this before about something called beads on a string, and this is a characteristic of pockets of gas of where new stars are being born inside the cluster. And is this one of those things? Is that a bead on a string, or is
We
that?
think so. We think so.
Okay.
So we think that if you look at just the bare bones HST image without the Spitzer image overlaid, you can see it a little bit better. But if you look at the central, the really
Do you have that
narrow,
handy, Scott?
I don't think so. I think we've only got the.
Oh, okay. All right. Okay.
I'm talking about really the raw data.
I see. Okay.
If you look in the center regions where the tail comes out from the central cluster galaxy, you'll notice that along there's these sort of equally spaced clumps all the way along before the whole thing kind of blows up.
Oh, yeah, there they are.
And that's what we call beads on a string. And it's the same kind of physics, really, as beads collecting on a string, sort of these clumps of condensation along this line.
Okay, now, because I'm a man-child and I'm infantile, this part made me laugh. But this is what you're calling a wet merger, is that correct?
Yes. Yes.
Oh my God.
Can we not invent that term?
Can we mute him?
But this is simply a state. Is what you're describing when it's gas, which I guess is somehow characterized as wet, being involved in a star-forming region like this, right?
Well, that's right. So what we're seeing. So just to be clear, what we're seeing with the HST image is not the gas, but the stars. But we know that there has to be gas there because there's so much star formation going on, and the stars have to be forming out of gas.
So between the infrared wavelengths, which are generating the heat, and the visible light, which we see here in Hubble, there's a lot of other physics going on.
There's a lot of other physics, that's right.
Okay.
Which we hope that's sort of one of the next things that we'll do is get a picture of the actual gas.
Okay, so when there's lots of gas involved, that's a wet merger. But the dry ones, are they just they still have gas because they
no.
are creating, they just don't, there's no stars being created.
So what a dry merger is, and it's been known for a long time. Well, it's been known that brightest cluster galaxies can grow through what are called dry mergers. And a dry merger is when two galaxies merge, but they're old elliptical galaxies, and neither one of them has very much gas to bring to the table, essentially. And so there's no fuel there for new star formation. Whereas in a wet merger, at least one of the galaxies is a galaxy more like our own Milky Way with a lot of gas. And that gas is then compressed and funneled and channeled during the merger to form new stars. So both are kinds of mergers where two galaxies collide together and eventually form one larger galaxy. But in the dry merger, the stars just kind of come together, and in a wet merger, there's new stars being formed.
Okay, so
and it's the wet mergers that haven't been seen before at the centers of clusters.
Okay, so yeah, and this is something that you expected to find, as you say, but haven't yet, and this is one of the first times you've seen one of these. I guess. So there's a quick question in here that's been sitting for a while. I want to ask. This is about the galaxy cluster. This is from John Glasgow on the Q&A app. He's going, is the pinwheel galaxy, which is M101, and he even knows that it's 6 megaparsecs away. Good job, John. Is the pinwheel anywhere near this cluster, or is this cluster much farther away? Now, the pinwheel galaxy is one of the most detailed images of a spiral galaxy that Hubble's ever taken. But where is it? Do we know where it might be with relation to M101?
Oh, gosh.
Do you mean on the sky or in terms of distance?
Well, it's in Ursa Major, I believe. And so, is it anywhere nearby other than just say it's in the same constellation? Or is it not really a part of the cluster?
No. Pinwheel's a relatively nearby galaxy.
Okay. So these are much further away then.
Yes.
All right. Thank you, John. That was a good question. Let's see. are there other galaxy clusters as part of the survey that you're looking at, or are you going to continue looking more closely at this particular one? Is there anything more that we can learn from this, both with other, say, wavelengths or other observations that you might want to make?
Yeah, so we're doing both. We're actively trying to study this particular object in more detail. So like I said, one of the things we would like to do is get an image of the actual gas within this system and see where the gas is and what the gas is doing. And so we have some proposals in to do that as well. And we'd like to learn more about the cluster as a whole. We'd like to confirm more members and get a better measurement of its mass, so we know exactly what we're dealing with. But at the same time, Adam's survey has produced hundreds and hundreds of galaxy clusters at large distances from us. And many of them show evidence that they might be similar systems to this. And in what way?
I just want to get Adam to comment on that a little bit.
Yeah.
So what are some of these characteristics that you're noticing, and other? Are you looking primarily for bright spots in the infrared, or what are you looking at?
Yeah, well, that's precisely it, right? We are looking for things that are really red overall. So when we did the thing with the Canada-France, you want them to be not very bright in the optical, and then in combination to be very bright with Spitzer. So big lumps of galaxies that are bright in Spitzer and not very bright in the optical. And we have found, as Tracy said, a few hundred of them. I think what she's referring to is, Tracy is a very prolific scientist, and she also wrote a paper in the last couple of weeks where she looked at some of the other brightest cluster galaxies and some of the other clusters we found. And what we're finding is that while this kind of thing that we're talking about today is very rare, particularly nearby, as we start looking at more and more of these very distant clusters, it's still uncommon, but it's not completely uncommon. So there's some other clusters in our survey where the central galaxy has potentially very high star formation rates, just like this one.
Cool. Okay, so Andrew Planet's got a good question I want to ask real quick, and that is, if these galaxy clusters contain supermassive black holes in their centers, could star formation be due to the constituents condensing from black hole high-energy jets forming gas fuel for new stars in the process? Is that at all possible? So, what are are black holes playing any role in star formation, either feeding it or causing it to condense in these galaxy clusters?
So that's another really good question, and I didn't mention this at all, but we do know that we suspect strongly that there is a black hole at the center of this galaxy cluster, and it's also contributing to the infrared emission that we've been mentioning, the intense infrared emission that we see from it. It's not dominating. Most of the energy that's being produced in the infrared is coming from star formation, but there is a black hole there. Whether or not the black hole is causing the star formation is an interesting idea, because, in fact, black holes are usually invoked in these situations to do the opposite, to actually stop the star formation. So the feedback from, so your listener mentioned these jets that come out of the black hole, the radiative and mechanical feedback that comes from the accretion disk and all the other activity that's going on around a black hole can actually disrupt the star formation and blow the gas out of, keep it from condensing and forming new stars. And so we think that if the black hole in this particular cluster is allowed to grow, it might actually stop the star formation that we're seeing.
And that might be why these things are so hard to see, period, right? I mean, in most galaxy clusters, it could be these black holes are disrupting a lot of the star formation.
It's a good question. So one of the questions we were trying to get at in one of the papers was, what was essentially the duty cycle? How long does the star formation go on for before an AGN shuts it down? And you can,
AGN is active galactic nucleus.
An active galactic nucleus, a black hole. Mm-hmm. And so the fact that these things appear to be quite rare may be telling us that the black hole shuts it down very rapidly.
Okay, good question, Andrew. Thanks as always. And Cecil Morgan's asking, what instrument, this is from the Q&A app, what instruments would be used to see the gas? Presumably the infrared showing you not the gas, but the heat coming from the star formation. And Hubble, the infrared or the visible light, are showing the stars. What could you use to see the gas with?
So for that, we're hoping again to use a spectroscopic instrument on the Keck telescope. Essentially, what we need to do is get what's called a spectrum of the galaxy, and that's the same, and the regions surrounding it. That's the same kind of observation that we do to get a redshift. And there we're looking for emission that's coming from the gas. So we're looking for the hydrogen lines and the oxygen lines, basically using the same kind of physics that people use in neon lights to try and see the gas in that way. So it would be a ground-based optical and infrared spectrograph.
Cool. Yeah, that's important. I don't know if you've ever done that lab experiment where you've looked at a tube, like a spectrum tube through a little pair of glasses, and you can see the lines coming from it. It's something very similar. It's the bright lines that the bright and dark absorption lines coming from a spectrum that tell you what elements are in that gas and whether there's gas present. So, good question, Cecil. Okay, I want to point out one little thing that I noticed when I was reading about it. It was a good comparison of the star formation rates. Apparently, according to what you guys have found, this little region is creating about 860 new stars a year, and by comparison, our Milky Way galaxy generally forms only about 1 or 2 stars a year. So this is quite a bit. This is a huge increase in star forming activity.
Yeah, that's right. It's I mean, I think maybe Allison can comment on this a little better than I can, because she was the one who made that measurement.
I love that idea. Go ahead, Allison.
Yeah, well, so basically the way you can calculate this is by using all of the data that we've been talking about, but particularly at the infrared and sub-millimeter wavelengths, which, as Carol mentioned earlier, really is tracing the dust that's being heated by the stars. So once you have the UV radiation coming from a star, it heats all this dust and it re-radiates in the infrared wavelengths. So when you have multiple wavelengths from different telescopes, all in the infrared and sub-millimeter wavelengths, you can get a pretty good estimate of the star formation rates. So that's what we've done with Herschel and the JCMT and Spitzer. So those are the primary instruments we use to measure the star formation rate, and yes, it's forming about 860 suns per year.
Cool. So Carol, I have a question for you, Carol, and I don't know if this may be totally dumb, but I'm going to ask it anyway. And the ultraviolet, which Hubble has got an instrument on that lets us see in that wavelength, could you see anything in the ultraviolet, do you think, in this situation, or no? Because doesn't it say something about stars forming?
Yes. Well, I mean, they have an observation of it, which I don't have. But sometimes it depends. It depends on how much dust is in the system. If they've got a lot of dust in front of whatever the UV radiation is, then you're not really going to see it. So I haven't seen the pure Hubble image, but it just depends. If you don't have a lot of dust in the system anymore, you could get a lot of UV radiation coming out. So it just depends on the circumstance of the object you're trying to look at.
Have you thought about that wavelength, Tracy, or is that probably not going to work here?
Well, so in fact, the image that you're seeing with Hubble is pretty close to the ultraviolet. It's taken in the infrared wavelengths, but because of the redshift, because of the great distance that this cluster is from us, what we're actually seeing is light that was emitted in the UV.
Oh, good point.
So these are actually the young stars that we're probably seeing in this tail.
Awesome. Okay, well, thank you for that. All right, I think, Scott, I'm looking around, and oh, wait, here's one from Andrew Planet. I'm going to ask you in a minute for Twitter, so let me get this question from Andrew again. He goes, thanks for the answer. He's the one that asked the black hole question. What eventually happens, then, to all the material that makes up high-energy jets? So I think these jets are assumed to be producing if they're actively, well, if they're active, they're feeding on surrounding material. So first of all, are there jets here? And if so, what happens to all that stuff?
So I'm not an expert on black holes in the centers of galaxy clusters. I don't know if Adam feels any more comfortable with that than I do.
What about you, Adam? Do you feel like hey, at least I'm not asking you to calculate sending things on in terms of.
I mean, I can go on about it, but if Adam more.
Okay, well, why don't you just say what you were thinking, and then we'll see if that answers this question.
Well, I mean, certainly we don't see any jets in this image yet, but we haven't really looked at the right wavelengths. So it is possible that there might be some jets there, and we have a proposal into the Very Large Array, which is a radio telescope, to see what kind of radio emission is coming from this thing. We're hoping also to get some X-ray observations, possibly from Chandra, to see if there's any signs of black hole activity as well. So as to what happens to all the material that's blown out from the jets, I think what happens is it goes out into what we call the intercluster medium, which is all of the gas and material in between the galaxies within the galaxy cluster. So when we have a galaxy cluster, there's a whole bunch of galaxies that you can see, there's a whole bunch of dark matter holding it together, and then there's also a lot of hot gas. And so the material that's being blown out from the center of the galaxy cluster will form part of this intercluster medium. But I have collaborators who study this a lot here in Montreal, and they see all sorts of wonderful images in the X-ray of huge holes and cavities being blown out within the intercluster medium that they think are being caused by these jets just basically clearing away material. So it's a very violent place, and how it all settles down, I think, is an open question.
Yeah, that's a good question, and it highlights the importance of all the wavelengths you can get to bear on a particular area of the sky is always useful, right? Mm-hmm. Okay, so Scott, do you see anything on Twitter? Is there anything we should mention on that?
It's a question that we've touched on and we've kind of danced around, but I'm really sorry.
There's no dancing on these Hangouts.
Yes, there's dancing. You just don't know it. But I'm so sorry if I mispronounced your name, but Noor Trebelsi, she's wondering how we're able to measure the redshift. So we've talked about spectra, but how were you able to, and this was back before we were talking about how the two blobs in the lower left were actually foreground objects, and she was wondering how you were able to find out, how you're able to measure the redshift to find out that it is a foreground object.
Adam, do you want to take this one?
Yeah, sure. It's once you get the data, it's a fairly straightforward thing to do. What we're looking for is, Tracy mentioned before, these emission lines that you see come from gas and come from or absorption lines come from stars in the galaxy. And so when we get a spectrum, we see a series of absorption features and a series of emission features. And what we do is we know what wavelength we would see them at if they were here on Earth. And of course, because they're not here on Earth and they're very far away and they're redshifted and they're moving away from us, the wavelength that we see them as has been shifted into the red. And so we simply compare all those wavelengths that we know, all those features that we know, the wavelengths that we measure to the ones we know they should be, and that difference is the redshift. And from the redshift, based on knowing stuff about the way the universe expands, we can tell how far away it is.
Right, and another interesting part about this whole thing is the fact that the wavelengths, what Tracy was talking about earlier, the fact that these stars were burning bright in one wavelength as the universe expanded and they got further away, they shifted the wavelengths of those light into the lower wavelengths of infrared, which I think it's always kind of blows my mind a little bit.
And so when you have the what Tracy very early on said is a two-dimensional image, so you have this two-dimensional image which gives you like X and Y. To get the Z, then you look at these redshifts, and depending on how close the cluster is, sometimes you can get enough resolution not only to tell that all those objects have the same redshift and another object is in front because it's not as far away. Sometimes you can actually tell the individual motions within there, so you know how far away, and then they have little bitty motions relative to like this big massive central thing. So it just depends on how far away it is, how much light it puts out, the resolution of the spectrograph, all those combinations, but certainly telling a foreground object from the cluster object is fairly straightforward.
Yeah, I can add, that's actually what we do. We do see those extra little wiggles on top of it, and those extra little wiggles are the galaxies moving around inside the cluster. And for measuring that, that's actually how we figured out how much mass is in the cluster, and that's how we know this is, 100 trillion suns worth of mass in the center of this cluster.
Okay. Adam Synergy, I see you there. You're a longtime viewer. He's on the Google Plus event page. He's saying that he's having trouble watching on Mrs. Synergy's iPad today. Is that your real name, Synergy? That's really cool. The Q&A app doesn't want to play nicely, so you folks have a day off from my crazy questions. So you guys got a reprieve. Adam, generally...
I did tell him he can get us on Twitter, but I've not seen him on Twitter yet.
Okay.
Synergy. I want that last name. Okay. Okay, well, Scott, anything else? Am I missing anything? Did you get it all?
No, that's anything's been already asked or answered in the Hangout. It's been really great as far as our interaction on there. Let me check YouTube real quick to make sure we haven't missed anything over there.
Yeah, I keep forgetting to do that.
Are you kidding? We solved all the mysteries of the universe?
In less than an hour.
No.
In less than an hour.
That's right.
We should get a bonus.
We should. No, we should get wine served to us.
Yeah. Well, we know that.
I know
that the Italian contingent.
Some people maybe already getting there.
Yeah. The Italian contingent, they're getting ready, I'm sure.
We won't mention who those people are.
Well, we didn't even we didn't get our word for the drinking game this time around either, but maybe next week. Okay, well, folks, I guess we're gonna call it there. Tracy Webb and Allison and Adam, I want to thank all of you for joining us today and sharing with us your research on this galaxy cluster. And hopefully, when you get more wavelengths, you'll come back and show us what you found or give us an update on what's happening. Well, will you do that for us?
For sure.
Awesome, great, thank you so much. Okay, guys, I guess that's it. On behalf of Scott Lewis, Carol Christian, I want to thank you all for watching. We will be back next week, same Hubble time, same Hubble channel, and come up with a new Hubble name. Oh, wait, Hubbleaholics, that was mine. I came up with that one this week. So
I'm still done with Hubblers.
I know. I'm still a Hubble hugger.
Yeah, I know.
Yeah, that's right.
Hubbleaholics has too many negative
Hubblers new, yeah, right.
Yeah, Hublandos. Okay.
Hublandos. Okay. All right, folks. I think the word was actually squishy.
Squish.
Yeah.
Oh, was that our? Well, we didn't.
We didn't
say it.
Tony, you can be my squishy Hubble hugger.
Oh,
no.
Yeah, that's just gross. All right,
okay,
folks.
I think we're done.
Thanks to all of you for watching. We'll see you guys next week, and as always, keep
looking up.
I almost said Dr. Scott Lewis.
No.
Scott Lewis from knowthecosmos.com and a great many other places around the internet. He's driving the internet for us during these hangouts. And why don't you tell everybody, Scott, how they can interact with us?
Yeah, absolutely. So the best and easiest way for you to interact with us is using the Q&A app. So while we're live right now, you'll see on the bottom left of your screen some yellow text saying that we are answering questions. I've got it loaded up. Tony's got it loaded up. If you have any questions for us and our guests, or even some comments about that, you can ask that in there, and you can even +1, you can bump them up. So if there's a question out there that you like and you want to have answered, you can go ahead and recommend that, and we can select it when it's live, and it'll let people know that we are answering that question that's going on. You can also comment on YouTube and also on Google+. We have a Facebook event for this as well. And the other great way for interacting with us is over on Twitter. So as you see in my lower third here, we have the Hubble Hangout hashtag. So I've got Twitter up right now over in TweetDeck, and we'll be answering questions, and I'll be live tweeting as we're going on. So just either @mention Hubble Telescope or use the hashtag Hubble Hangout, and we will get your questions and reply to them during the show.
And I want to remind you guys that it's starting to happen more often now. People are telling me that they can't find the Hangout, and the best way to find it is to subscribe to us on Hubble Site channel on YouTube, and that will alert you when the ones are coming out live. But you guys should know by now, every Thursday at 3 o'clock Eastern Daylight Time, we are here doing Hubble Hangouts, and so you should always check out the channel there. You could also follow us, like Scott said, on @Hubble Telescope. So those are the two easiest ways to find out about these Hangouts, and you know you want to find them because they're becoming world famous. I was looking at the demographics the other day. Hubble huggers, Hubblers, Hubbleholics, whatever you want to call yourselves, all of you guys are all over the world watching these Hangouts, and I think I know why. We were talking about this also before the Hangout. You know why? Because where else in the entire internet are you going to learn what the mass of a blue giant star is in units of cows?
Cows.
That's right.
Or the energy of a quasar, of the energy of a quasar in units of ant push-ups. These are the kinds of things, folks, we've made astronomers do in the past. And where
highly scientific.
Entire internet are you going to find something like that going on?
And now our guests have just left because
that's right. We
they
make
don't want to do those calculations.
We make you guys earn your degrees, right? It's like, yes, it's great that everybody has.
And I just want to comment. I don't know why people can't find Hubble Hangouts. It's called Google.
I know people. Also joining me is Dr. Alison Noble. She is from the University of Toronto, and Adam Muzzin from Cambridge. Welcome to both of you guys. It's good to have you on our Hangout.
Thank you.
Hello.
Okay, so let's get started.
And by the way, we really appreciate them being here visiting us from Italy.
Oh, really?
Italy.
It's
Yeah. They're at a conference in Italy.
Oh, you're in Italy right now?
Yeah.
Yes.
Oh, okay.
Yes, we need to clear a very busy schedule.
Yeah, we could be having a glass of wine.
Oh, you don't know how. I know
we didn't stop you from having a glass of wine.
That's right. In fact, we're gonna probably come up with a word for a drinking game soon. So you might want to stay tuned.
It would not be a first time we've had a drinking game, but drinking espresso shots. Yeah, let's put it in the chat.
Which is the last thing any of us need right now.
Right.
Okay, so today we put out on Hubble site and as well as went out into the internets in general a press release that was announcing some of these findings, some of these observations. So Tracy, I think I'd like to start with you, but I also want to. We always wait too long to put up images. So Scott, if you'd go ahead and put up this image, this is a galaxy cluster. And Tracy, can you describe a little bit what we're looking at here?
Yeah, so what you're seeing is, I guess, a side-by-side image. Obviously, but I'll just make it clear, the image on the right-hand side is
Hubble Hangout. And there are like 5 links to YouTube, to our website, to all things. So,
yeah, I agree. But still, nevertheless, people say they search for it, can't find it, so I'm trying to help them in any way I can.
It's not rocket science.
Yeah, you know what I'm going to do in the next exoplanet hangout? I'm going to ask the guests to tell me how many chewed up pieces of gum that would fit in a Neptune-sized exoplanet. That's what I want to know next. So stay tuned, folks. We'll find all that out this week.
Yeah, that might be next week. If I can drum up some exoplanet people.
So this week we have a very interesting hangout in store for you, and if I haven't scared away my guests, although it looks like I have almost scared away one of them already, don't worry, we're not going to make you do any weird calculations this week unless...
I will. I'll make you do them.
Oh, okay. Okay. I was going to be nice, but, Scott's...
I'm never nice.
So as I mentioned at the top of the hangout, astronomers using both the Spitzer Space Telescope and Hubble, and I guess the Canada-France Hawaii Telescope, which is on the ground in Hawaii, were looking at this galaxy cluster, and they found something. They looked at something. They found things that surprised them, and I'm going to let them describe what that is. But before I do, I've got to introduce them. With me is Dr. Tracy Webb. She is from McGill University, astronomer in Montreal. Hi, Tracy, and welcome.
Thank you very much.
Hello, everybody, and welcome to this week's Hubble Hangout. My name is Tony Darnell, and I work at the Space Telescope Science Institute. It makes me very happy to welcome you all back to our Hubble Hangouts here because you guys have been giving us all kinds of great feedback and it's just been amazing. We were just talking before the Hangout. We've been doing this for 2 years now. So every week we try to bring you new science from the Hubble Space Telescope, and we are here today with yet another example of that. This week, astronomers using both the Spitzer Space Telescope and the Hubble Space Telescope have been looking at galaxy clusters, and they have found something interesting in there that ordinarily they do not find. I'm not going to give it away yet because we're going to have the astronomers tell you all about it. So now this is ordinarily the time when I start giving out announcements and stuff, but I don't have any, so because I don't think anything all that interesting was going on, so I'm not going to pass it on to you guys, but I would like to invite you guys to leave questions and comments throughout the Hangout, and we will read them throughout, and I'm going to have Scott tell you about that in just a minute. But first I have to introduce my partners in crime, Dr. Carol Christian, who joins me. She's the HST Project Outreach Scientist. Hi, Carol. Also joining me is